Hey everyone, let's dive right into this study guide explainer. We're going to unpack the absolutely crucial concept of statistical dispersion, so you can totally ace your next data analysis exam. If you've ever looked at a data set and felt like it was kind of hiding something from you, well, you're probably right. So today, we're going to learn exactly how to uncover the full story behind those numbers. Here's our roadmap for this explainer. First, we'll be defining statistical dispersion. Second, we'll look at the significance of dispersion. Third, absolute measures explained. And finally, relative measures explained. All right, moving right along to part 1, defining statistical dispersion. Let's see how this builds our foundation.
So before we hit the formal definition, I want you to ask yourself a question. Are averages really telling you the whole truth? Because when you're analyzing data, you have to realize that a central average, like a mean or a median, can actually be highly misleading if you don't know how wildly the individual data points are scattered around it. Just imagine two data sets, right? Both have an exact average of 50. But one consists of the numbers 49, 50, and 51, while the other consists of 0, 50, and 100. The average is identical, but the reality of that data is completely, radically different. And that brings us to our hero metric, which is dispersion. Formally, it's defined as the degree of heterogeneity within a dataset, describing the spread or scattering of individual values around a central tendency. Okay, in plain English, dispersion measures exactly how much, on average, individual items differ from that central value. It basically quantifies the chaos or the lack of chaos in your numbers. Now that we know what it is, let's jump to part 2, the significance of dispersion, and why measuring this spread is literally the foundation of all advanced stats. The crucial point to remember for your exam is that measuring dispersion isn't just some busy work your professor assigned. It has 4 massive real-world applications. Number 1, it determines average reliability. It proves if your mean is actually representative. A low variation means your average is super trustworthy, while a huge variation means it's practically useless. Number 2, it facilitates comparisons between different distributions, so you know which dataset is more consistent. Number 3, by mathematically isolating this dispersion, you can find the underlying causes of the variation and actually take steps to control it. And number 4, it enables other statistical tools. You quite literally cannot perform correlation, regression, or deeper statistical inference without first understanding the dispersion of your data. With the why covered, let's jump into the climax of our study guide with part 3, absolute measures explained. Here's the definition you need to know. Absolute measures are measures of dispersion expressed in terms of the original units of the data being measured. So your key takeaway here is that absolute measures carry specific units. If you're measuring distance in kilometers, your absolute dispersion is in kilometers. If you're measuring weight or currency, your dispersion is in kilograms or rupees. Because of this, they are completely unsuitable for comparing the variability of distributions that use different units. Plus, even if the units are exactly the same, absolute measures still fail if there's a significant difference in the average values of the datasets you're comparing. As for examples of absolute measures, these are the classics you're going to see on your exams: range, quartile deviation, mean deviation, and the highly popular standard deviation. When you calculate these, remember that you are generating an absolute measure tied directly to the original data's units. They are fantastic for understanding a single data set in perfect isolation, but they totally hit a wall when you need to look at the bigger picture. But what happens when we need to compare apples to oranges? That brings us to part 4. Relative measures explained. The brilliant solution here is relative measures. The definition? They are pure numbers expressed as ratios or percentages, entirely independent of any unit of measurement. So, by taking the ratio of an absolute measure and dividing it by an appropriate average, the units simply cancel out. What we're left with is a unitless relative measure, which is the absolute gold standard for comparing the spread of 2 or more completely different datasets. Now, for examples of relative measures, they directly correspond to the absolute ones we just talked about. But because they are pure ratios or percentages, they are often referred to as coefficients of dispersion. A great tip for your test: if you see the word coefficient, immediately think relative measure. You have the coefficient of range, the coefficient of quartile deviation, the coefficient of mean deviation, and, crucially, the coefficient of standard deviation. And fun fact, when that last one is expressed as a percentage, it's famously called the coefficient of variation. Okay, if you're going to mentally screenshot just one concept for your test, Make it this fundamental comparison. You absolutely have to contrast the heavily restricted, unit-bound absolute measures against the highly flexible, unitless relative measures. Absolute measures keep their original units, meaning they fundamentally fail at cross-unit comparisons. Relative measures, on the other hand, give you pure numbers or percentages, making them the standard tool for comparing totally different data sets side by side. Honestly, knowing when to use which is the difference between a total novice and a true data analyst.
As we wrap up this study guide explainer, I want you to think critically about this final question. If a real-world study only gives you absolute measures, what crucial truths about data variability might they be hiding from you? Ignoring relative dispersion could lead you to make terrible analytical mistakes out there in the real world, like misjudging a massive risk simply because the raw unit numbers looked small, without factoring in the overall average. Always look for the coefficient. Keep that in mind. Best of luck studying for your exams, and keep digging into the data.